Hello and welcome to your second before last chemistry lesson. So once again, the lesson is going to be 1 hour long. It will be recorded and the recordings will be sent to your parents. If you have any questions, please put it in the question and answer question box. And if you want to post answers, put it in the chat box. And yep, so the lesson tomorrow is going to be at 5 p.m. and that's going to be our last one, and we're going to be doing past paper questions and covering exam techniques. Okay, so let's start. So today we're going to be covering transition elements, but before that we're going to be talking about ions. So we may have already met the ion slightly yesterday when we were doing working with group 1 and group 7. So obviously when we lost an electron from the group 1s, we were forming the positive charged sodiums and group 1 elements. So these are called ions. So atoms, they are neutral to begin with because they have the same number of protons and electrons as we saw in lesson 1. But atoms, they can gain or lose electrons as we saw yesterday. So in the case of group 1, the atoms lost an electron, and in the case of group 7, atoms gained an electron so that they got to that stable configuration that they want. They want that noble gas configuration, don't they? Okay, so if an atom gains an electron, it ends up gaining an overall negative charge. So with the group 7s, we had, say, let's take fluorine. We know that it's got 7 electrons in the outer shell, and then it's going to gain an electron so that it ends up with 8 in its outer shell, which is its stable configuration. So if it's gained an electron, it gains a negative charge. So therefore, the ions that group 7, the halogens, form are F-, or all of them form negative ions. So why does it gain this negative charge? Because now it has more electrons, which from lesson 1 we know has a negative charge, than protons, which have the positive charge. So if we look at the fluorine atom, if we draw out its electronic structure, like we saw yesterday, there we go, so 7 electrons outer shell, it's going to gain an additional electron. And because now in the nucleus, we know that it's still 9 protons, sorry. But in the outside, we now have 10 electrons. So therefore, we have 10 negative charges and only 9 positive charges. That's why when you gain an electron, you're going to form a negative charge on the ion. Okay? So here is what is an ion. If you want to quickly jot it down, but if not, this will all be put on YouTube and emailed to your parents. So you'll still be able to access these slides even after the lesson. Okay, so yeah, it's really important. Whenever an atom gains an electron, it forms this negative ion. Okay, however, if like in the case of group 1, it loses an electron or more, it becomes a positive ion, because now our atom will have more protons than it does have electrons. So if we look at our lithium, we use lithium as an example. So we're going to have 2 in the inner shell, 1 in the outer shell. How many electrons is it going to lose? It's going to lose 1 to get to its stable configuration. So now we just have 2 electrons. How many electrons did we have in the nucleus? We had 3. Sorry, how many protons do we have in the nucleus? We had 3. And in this neutral atom, we also had 3 electrons on the outside. Now we've lost an electron, so now we've got 2 electrons in the outside, but still 3 protons in the nucleus. Yeah, so therefore we have 3 positive charges and only 2 negative charges. Therefore, we have a positive overall charge. Yeah, do people have any questions? That's how ions work. Yeah, you can think of it like that. So an ion is an atom that has gained or lost electrons, and it's never neutral. Okay. So, so if oxygen is in group 6, it wants to gain 2 electrons. But what will be the charge of the ion formed? So it wants to gain the 2 electrons because it wants to reach 8 electrons in its outer shell. So obviously group 6 means it's got 6 electrons in its outer shell. So then what will be the charge of the ion formed? Yeah, 2 minus, because we had 8 protons to begin with and 8 electrons to begin with, but we have gained 2 electrons. So therefore now we have 10 electrons. Each electron, it carries a negative charge, and each proton carries a positive charge. So we've got 8 positive charges, 10 negative charges, so that's why it is a -2. Do 2 elements have an electrostatic charge? Is that why they bond together? So this is to do with ions. Elements don't. So if, say, NaNCl, they have electrostatic attraction because the Na's formed a positive ion, the Cl's formed a negative, and therefore the opposite charges they attract. So it's to do with ionic bonding. Okay. So yeah, so if, say, we took aluminium, for example, aluminium is in group 3. Do we know what kind of ion it's going to form? So is aluminium a metal, firstly? Yeah, so some people have got it right in the chat. Yeah, exactly, it is a metal, and we should note that metals, they lose electrons, okay? So metals always lose electrons to gain this stable configuration. So aluminium is going to lose electrons. How many electrons do we think aluminium is going to lose? Okay, so it's going to lose 3 electrons. Perfect, yeah. So if aluminium loses 3 electrons, we're going to get a 3+ charge, because now we're going to have 3 more protons than we have electrons in our atom. Okay, and that is where this charge comes from. However, if we say think about, so if we say take bromine, for example, has 7 electrons in its outer shell, how many, what's it going to do? Is it going to lose electrons or is it going to gain electrons? Going to gain, yeah, perfect. It's going to gain electrons. It's going to gain 1 electron to get to its stable configuration of 8 in its outer shell, and therefore it's going to have 7 protons in the end, but 8 electrons, and that is why it forms a negatively charged ion. Well done to everyone who wrote that. Perfect. Okay. So let me quickly go through the questions. Are all the metals in the middle in a group? That's not exactly how it works, but you don't need to understand those groups. So you just need to know your groups 1, 2, and then on the other side, the transition metals, it is 3, 4, 5, 6. Otherwise, the transition metals, you don't need to think about their groups. Which type bonds include ions? So that's going to be your ionic bonding, include ions. Yeah, okay. Hopefully that's clear. So next, we're just quickly going to talk through isotopes. So do they not have a group? In A levels, they probably will have a group, but in GCSEs, you don't need to know anything about their groups. So you just need to know the groups that you have learned so far. So only 1, 2, and then on the other side, it's 3, 4, 5, 6, 7, and 8. Okay. So isotopes. Hopefully, some of you guys have met these isotopes. So what is an isotope? So what to remember is that atoms, they of the same element, always have the same proton number. Okay, so the proton number never changes, but they can have a different number of neutrons in their nucleus. So atoms of the same element with different number of neutrons are called isotopes. This is a good word to remember. And they always have the same atomic number, but their mass number may differ, okay? So an isotope will always have the same proton number. It will always have the same number of protons and electrons, but its number of neutrons can change. Therefore, its mass number can change. You do not need to know anything about the lanthanides. That is far beyond, it's even beyond the A-level spec. It's like uni that you do lanthanides. So groups 1, 2, and 3 lose electrons. It's your metals, they lose electrons. Your non-metals gain electrons. Okay, so that's what an isotope is. So if we have, you guys might have heard of carbon 12 and carbon 13. These are 2 isotopes of carbon. So the number that's your mass number. So in this case, carbon 12, your mass number is 12. In this case, carbon 13 is your mass number of 13. And both of these have atomic numbers of 6. Okay, so if carbon 12 has a mass number of 12, how many neutrons does it have? So the mass number is 12, right? That means that is the total number of protons and neutrons. And we know that our atomic number is 6. So the atomic number is also the same as your proton number. So the atomic number is always also equal to the number of protons. So we've got 6 protons and 12 proton neutrons. Therefore, in this isotope, we have 6 neutrons. What about in this isotope? So we've got a mass number of 13. So that's 13 protons and neutrons. How many neutrons do we have in that isotope? Brilliant. Everyone who said 7, perfect. Because we do 13 take away 6, which is 7. Exactly. Okay, hopefully that makes sense. So different isotopes can have different physical properties. So that means that they can be radioactive, because it might be an unstable nucleus. But not all isotopes are radioactive. So that's one of the potential properties of an isotope. And they will also have different densities. So the two differences. So there's the two physical properties that may be different depending on what isotope you have. Okay, but their chemical properties will be the same. So an isotope is the same element, so that means it has the same proton number, but it has a different mass number. So if we look at this one, there's 2 isotopes, right? Carbon 13 and carbon 12. So carbon always has a proton number of 6, always has an atomic number of 6, which are the same things. However, it might have a different mass number. So in this case, in the top one it's 12, in the bottom one it's 13. What this means is that they're going to have different number of neutrons. So an isotope has the same number of protons, but different number of neutrons. Okay, you can have physical properties that are different. It may be radioactive, and it will have different densities, but their chemical properties will be the same, as they have the same electronic structure. Because atoms of the same element, so the isotopes, they're going to have the same number of protons, so therefore the same number of electrons. And all your chemical reactions and their reactivity is determined by their electronic structure. Okay. So now let's move on to transition elements. So all metals positioned in the large central block of your periodic table between group 2 and 13 are your transition elements. Okay. So So physical properties of transition elements. They're good conductors of electricity and thermal energy, so very similar to your typical metals. They're hard and strong. They have high densities, high melting points, apart from mercury, which is a liquid at room temperature. Some of you maybe have seen it at school. It's quite a cool element because it's a liquid metal. But yeah, so these are the typical properties of metals and of your transition elements. Okay, compared to group 1, they are much harder, much stronger, and a lot more dense. As we learned from yesterday, group 1, they're quite light ones. They float on water, don't they? And they're really soft because you can cut them with a knife. However, transition metal elements, you definitely can't cut them with a knife. They're much harder and much stronger. So if I'm going too quickly through the slides will be put up and you'll be able to see them on YouTube and write that down. So why are metals hard and malleable in terms of atoms? So malleable means that they can be like stretched, aren't they? So they're malleable because of the layers in metals. So metals are arranged in these perfect layers. And when you put pressure on them, they can slide across. The layers can slide. So this is slide 10. And yep, so transition elements are far less reactive. Yeah, brilliant. Joe answered that other question. Why they're malleable? Because the atoms can slide over each other. Okay, so let's move on then. Yeah, look here, we talk about the reactivity. So they're much less reactive with group 1. As we saw and heard yesterday, group 1, it was stored in what? It was stored in oil to prevent it from being oxidized, exactly. So in the case of transition elements, they're everywhere. They do not react readily with oxygen or chlorine or water. We saw also group 1, they had that vigorous reaction with water, and you could see the fizzing, and it was like super fast. However, transition elements, they are significantly less reactive than your group 1. So look, for example, copper must be heated before it reacts with oxygen in the air. So you need to heat this in order to get to copper oxide. Okay, so look, the process with chlorine is also a very slow reaction. We need to pass chlorine gas over iron and heat it very strongly. And then some of you hopefully have seen a rust. Well, hopefully you haven't, because rust isn't good. But you know that like weird color that forms on metal, so that's rust. And that happens very slowly. That's why you can make stuff out of iron, because although they might rust in the air, it's a very slow process because our transition elements, they're really unreactive. I don't really understand your question. Is this only with gases to solid? So this lesson is on transition elements. Okay, so that bit in between group 2 and group 3. So you've got your 2 blocks. It's right in the middle. Here's group 1 and group 2. Here's the other ones, and then your elements in the middle. That's your transition elements. Okay. So yeah, key things to remember is that they're not reactive, they are hard, and they have high densities. So we're going to do a Kahoot as soon as we finish this content. It's quite a long Kahoot today, so got that to look forward to. So we use transition metals as structural materials because they are chemically unreactive, as we've just said, and their physical properties because they're so hard and strong compared to, say, our group 1 metals, which we could cut with a knife. So that'd be really unuseful. So we should try to find a periodic table. I want to show you guys. I don't know what periodic table is. Oh yeah, okay, here we are. So some of you guys are asking what group do these transition elements belong to. So your transition elements, what you need to know are the elements between group 2 and group 3. At GCSEs, they do not have group numbers. You do not need to number them, okay? So you just need to know they're these elements in between group 1 and group 3, and that's it, okay? Makes sense? Okay, so let's carry on. So yeah, reactions are really slow because they are very unreactive. So the properties of transition metals, they're strong, they're hard, they're also unreactive, and they have high densities. Yeah, brilliant. The ones between group 2 and group 3 are transition metals or transition elements. Brilliant. So, yeah, we just said that they're useful in structural materials. So compounds of transition elements. Compounds of transition elements are colored. Some of you hopefully have seen different colors of them. So, for example, copper sulfate is blue. Hopefully some of you guys have seen this. And this is because of this Cu2 plus ion formed. Okay. Nickel carbonate is pale green because of this ion. chromium oxide, dark green because of the ions. So it's all to do with the ions that determines the colour. And yeah, they're really pretty, the transition element compounds. So name of compounds with transition elements include Roman numbers. So it's these numbers that we're talking about. Do you need the colours of the elements? Sometimes copper sulfate, the colour of that does come up. It might be just good to remember that copper sulfate is a blue, that copper in general forms blue compounds. So that may come up. So we're going to have some questions with transition metals later on. So yeah, these Roman numerals, they tell you the ion that is formed exactly. I think someone said that. So we need these Roman numerals because transition states can form more than one ion. With our group 1s that we saw yesterday and our group 7s, we knew exactly which ion was going to form. So in our group 1, we knew that all those ions were going to form a positive charge. Yeah? And that all of the group 7 ones were going to have them with a negative charge. So that was certain. We knew group 1 forms our positive ones and group 7 forms these negative ones. However, with transition elements, they can form more than one ion, as seen here. So iron can form both iron 2+ and iron 3+. Okay, so these Roman numerals, they're telling you what the ion is. So in this case, iron 3 oxide, we know that it is this ion. If we say had iron this oxide, which one would it be? Which ion would it be? Sorry, it's so messy. You have any ideas? Yeah, brilliant. So it'll be Fe 2+, exactly, because this Roman numeral, it tells you what ions will be. Okay, so like with copper, we can form copper plus or copper 2+. Chromium, we can also form chromium 2+ or chromium 3+. There's a couple to remember. Okay. So then, another thing to remember, just another fact about them, is that they're very commonly used in catalysts. And a key one is the manufacturing of margarine using nickel. So it might be good to remember that nickel is used for manufacturing of margarine, and iron is used in the Haber process to make ammonium. Okay, so those are your key things about transition elements. They are catalysts, so they're used in catalysts. They form coloured compounds. They form multiple ions. So ions can have different charges. They're also hard and they have high density. So I'll look at some questions. Yeah, so this slide is about transition elements because transition elements can form catalysts. So they're what's used to form these catalysts. So the plus always goes after the number, yes. So in ions, the plus always goes after the number. So in oxygen, like it forms an O2 minus. Fe, it's Fe2+. So your plus and your minus goes after the number. What's meant by forming more than one ion? So like I tried to explain, with our group 1 that we saw yesterday, we know that our group 1 are going to form ions with a positive charge. So we know that sodium is going to only ever form an ion that is Na+. Potassium is always only ever going to form an ion that is potassium+. Okay? Just the same way that chlorine will only ever form an ion that is Cl-. However, what transition elements can do, they can form ions with different numbers here, with different charges. So as we just saw, iron can form ions with Fe2+ or Fe3+. So that means it's formed two different ions. Yeah? So that's what it means by transition metals can form different ions. Does that make sense? Okay, look at the questions. So can ions have a negative charge or a positive charge? So non-metals, they form negatively charged ions, because when do you form a negatively charged ion? It is when you're gaining electrons. Yep. So we know that group 7, they gain an electron, so therefore they form a negative ion, because it's got one extra electron, and that's where the negative comes from. However, in say group 1, we know that they lose electrons, so they're going to form this positive ion. Okay, so you can have both negative and positive charges of ions. Is it possible to have a +4 ion? Yes, it is, but that's not something you need to know in GCSEs. If it is an oxide, will there be some rust? So rust is iron oxide, so FeO, iron oxide. That's what rust is. What is margarine? Margarine is what you spread on your bread. So it's just what you eat. So confused with the Roman numerals bit. Should we know what ions they form? No, you don't really need to know that. You just need to know that they can form different ions. Dun, dun, dun. Are all metals arranged in layers? Yep, so that's the metallic structure. So I think metallic bonding comes up a bit later on in your GCSE course. And that is, yes, so all metals are arranged in these layers, so that the spheres are arranged in perfect layers that can slide over one another. Do you have to memorize the periodic table? Absolutely not. Let's go to the notes. Yes, sure. Is there any elements that can be both negative and positive ions? That's university level question. So what you need to know is just no. So what you need to know is non-metals, they form negative ions, and metals, they form positive ions. Yeah, so the ion does determine the color of the transition metal. Well done. Perfect. So most complicated question that can come up with transition metals, we're going to be doing some questions soon. So hopefully you'll see. I don't really think that the questions get too complicated with transition metals. What is an alloy and a composite? Yep, they're based the same thing. So for group 1, does it matter if you make it positive or negative? Well, what's happening in group 1? So we've just said, is the electron gained or lost in group 1? So how many outer electrons does it have? It has one outer electron, yep. So to gain its stable conformation, stable electrons, it's going to lose this electron. So it's got 8 electrons in its outer shell. Yeah, so therefore it's lost electron, and that means it's a positive ion. Because now, if sodium has 11 protons, and at the start, the atom has 11 electrons, however, now it's lost an electron, right? So now it's only got 10 electrons, but still has its 11 protons. That means it has 11 positive charge, but 10 negative charge, which leaves us with an additional positive charge, and that's why we form a positive ion. Okay. What's the Haber process? It's just something that makes ammonia. Why are alloys harder than pure metals? Also, do we need to know cations and anions? I don't really understand which cations and anions you're referring to. And what was the other question? Oh, why are alloys harder than pure metals? So this is probably more in your like metallic bonding bit. I think it's a bit later on in the course, but we'll quickly go through it. So as I said, metals are arranged in these perfect layers, right? Sort of like this. These spheres should be the same size. However, mine are not. An alloy, that is a mix of metals, okay? So instead of having just say pure iron, you'd have iron and copper, okay? So iron and copper, they have different sized atoms. This means that you can't make it this perfect layered arrangement. And they're softer because you can slide these layers over one another. However, in an alloy, because the atoms, they have different sizes, you're going to get a disruption of this perfect layer. So say this is an over exaggeration. Say that's your copper ion here. and the little ones are your iron ones. So can you see you now no longer have these perfect layers? You can no longer slide this way. You can't push it and it slides because now you have this big ion, this big atom that's blocking it. And that's why alloys are harder than pure metals. What is nickel? Nickel's just one of the elements in your periodic table. It's just a transition metal. So we're going to see what kind of exam questions we're going to get in transition metals soon. Yeah, transition metals have a positive charge because they are metals. Brilliant. How many electrons do transition elements have? That's kind of irrelevant to us. We don't really need to understand that part, but it's whatever. So the proton number is equal to the electrons. So therefore, if it says like 20, it's going to have, if the proton number is 20, it's going to have 20 electrons. So I'm just looking through the questions. So are alloys stronger? Yep, definitely. Alloys are much stronger. Define and answer question related to cations and anions. Still confused by that question. I don't really understand what you mean. Can you balance ionic compounds to make them neutral charge? Yeah, so all ionic compounds are balanced so that they're neutral, like sodium chloride. We know that sodium has a positive charge, chlorine has a negative charge, and that's why it's sodium chloride, because the two charges, they cancel out, and now it's a neutral compound. Brilliant. I think this topic will be on paper 1, but I'm not really sure. I think it's going to be the first paper. Whereas the Haber process, that's just making ammonia. So you need to know about it. Alloys are a mix of metals. Okay. Can ions return back not being an ion? Yeah, that's just through a chemical reaction. You can do that. All transition elements are metals. Brilliant. So you can call them transition elements or transition metals if you find that confusing. This topic is called transition metals or elements. Okay. Do people have any more questions? Or we'll move on to the Kahoot. Yep, so we do have a Kahoot ready. Yeah. Why is Mercury not a solid? You don't need to know that. It's going to be to do with the intermolecular force, I think. Maybe not. Okay. So let's start the Kahoot then. So I'll give people a minute to join the Kahoot. People keep having questions, please put them in. So this Kahoot's going to cover a couple questions today, but also quite a few from the previous lesson. So it's a bit of everything, a bit of revision. And if you don't have access to Kahoot, please just jot down your answers and you'll see the answer at the end, so you can check yourself. Will there be any 6-mark questions on this topic? There could be. They could ask you about the properties of transition metals. They could ask you to compare compound 1 and transition metals, what the differences between the two metals are. So there could definitely be 6-mark questions. We're going to be covering a lot of past paper questions tomorrow. So hopefully I'll see you tomorrow, and we'll definitely do some questions on transition metals. I'm sorry, I think we should keep the volume a bit down. But I'm sure you can find the music on YouTube if you like listening to it. Yeah, this is C1, I'm pretty sure. In AQ at least. All transition elements are metals, yes. All transition elements are metals. Okay, so I'll wait 10 more seconds for the last few of you. When you're struggling, please just jot down your answers on a piece of paper and you'll be able to see the right one at the end. Okay, go another 5 seconds. Okay, let's start then. Everyone's ready. So chemistry 4, a 4th lesson. Transition elements are something compared to group 1 metals. Okay, let's see. Well done. So they are significantly less reactive, as we heard. Transition elements, they do not react with water unless you force them to, whilst group 1, they have that vigorous reaction that we heard about yesterday straight away. So they're far less reactive than group 1. Not very reactive at all. Well done to Snail. So common ions formed by copper are, what was in the PowerPoint? What did we see? Yeah, we will be going over exam technique tomorrow. Can we remember which of these were the common ions? Yeah, brilliant. So just as a fact, I don't think you need to remember this, copper plus and copper 2 plus, and copper 2 plus forms blue compounds. Okay, next one. So transition elements are which property? Brilliant. Okay, so we could have just done this one by a process of elimination. So we know they're not soft, we know they're not reactive, and we know that they are metals, so therefore it must be hard. Okay, so true or false? Transition elements are used to make catalysts. Yeah, brilliant. So it's true. Which processes was it? One was the Haber process to make ammonia, and the other one used nickel to make margarine. Well done to everyone who put true. Well done to Lal for coming first. So now this is a bit, so up to there was on what we've done today. Now this is a bit of recap. So what are the subatomic particles found in the nucleus? Yeah, brilliant. Whoever put it on. Well done. Well done, everyone. Most of you guys were right. So electrons, they're outside orbiting the nucleus. So in the nucleus, it's just protons and neutrons. Oh, we've had a swap. Well done to Anno. So maximum number of electrons that can occupy the first energy level. Or shell, well done. So energy level or shell, perfect. Okay. So brilliant, everyone who put 2, amazing. Well done for no one putting 10, because didn't fall for any tricks. Ooh, and another swap, well done to Thomas. So what about the second energy level or shell? How many can that hold up to? Yeah, brilliant. Whoever's putting it in the chat, great. Okay, so yeah, it was 8. 2 is in the first shell, 8 is in the second and third and beyond. And yeah, it's never 4, okay? Well done to everyone. Okay, so how can an atom become an ion with a 2+ charge? What happens when an atom becomes an ion? Yeah, brilliant. Well done to Harry. Well, perfect. Okay, well done. Most of you guys got it correct. So yeah, it's not it gains 2 electrons. If it's gained 2 electrons, what charge is it going to form? It's not going to be positive. It's going to be what? It's going to be a negative charge. Yeah, 2 minus, exactly. Perfect. So yeah, so when it loses electrons, that's when it forms the positive ion. Great. Oh, well done to Snail, coming back to the top. Okay, so a few more questions left. So atomic number is equal to the something in the atom. Yeah, brilliant. It is what the person in the chat said it is. Oh no, sorry. The atomic number is equal to the protons and the electrons. Question. So Thomas, well done for getting back to the top. So now back to our separation techniques. Yeah, so it can be 2 answers. You get it correct for either of them. Because obviously, although your atomic number, that is your proton number, but your number of protons is equal to your number of electrons in the atom, and that's why it is either of those answers, okay? Okay, so this one's confused some people. So firstly, let's start with paper chromatography. It's not paper chromatography because paper chromatography is more used to see what the different substances is in it. It's not really used to separate. Filtration, when's filtration used? So filtration is used when you have an insoluble thing in a solution or in a solvent, right? So if it's still a solid like sand and water, that's when you use filtration. However, we have a solution with potassium chloride which has dissolved in water. So therefore we can't filter it. And why won't we do evaporation? So this time we're actually separating water from potassium chloride. So it's really key to know that we want to keep the water. So with evaporation, where's our water going to go? It's just going to go into our atmosphere. It's going to evaporate and just, disappear. However, that means we're not going to be able to capture the water, are we? So in the end, we're going to be left with solid potassium chloride. So therefore, we need to do distillation in order to capture our water, which is what we're trying to separate from the potassium chloride. Yeah, so that's why it's not evaporation. Yeah, so if the water evaporates, it just goes into the atmosphere. It just goes into the air, and therefore you're not catching it. Whilst in distillation, you obviously cool down your water and then you capture it. So that's why you separated it. Okay. And the last question. Dun, dun, dun. Ooh, we had another swap. Basil boy. Oh, sorry, second for last. Which group do the halogens belong to? Yeah, well done. Lots of correct answers. Brilliant. Okay, so group 8 and group 0, what are their names? So that would be the noble gases. What about group 1? Is that next? Yeah, brilliant. So next, I think. Oh, well done, Thomas, coming back up. Last question, which do the group do the alkali metals belong to? So this is a bit self-explanatory now. I think just what we said. Yeah, brilliant. So we said that group 8 and group 0 were the noble gases. We just said that group 7 was our halogen. Therefore, our alkali metals are in group 1. Brilliant. Well done. Okay. Well done to everyone. Let's see who won the Kahoot. Well done to Shrew and to Chris. And then the winner is Thomas. Woo. Great effort. Well done. So let's go back to our questions now. So now we're going to do some questions on this topic. So now this is a transition metal question. So how would we be able to tell which compound was which if you were given unlabeled samples of copper sulfate and sodium sulfate? So do people have any ideas how they might be able to differentiate them? Brilliant, I can see a correct answer. So yeah, so it is to do with the color. Okay, so we know that transition metals, they form colored compounds. However, the sodium sulfate, yeah, so sodium sulfate will be blue. But the alkali metals, they form white precipitate, so they form white solids. Okay, well done to everyone. So why does copper in copper 2 sulfate have a Roman numeral? If people want to jot down some answers. But sodium and sodium sulfate does not. Yeah, okay, so almost. So Joe has said it right. So because copper has multiple ions, that's why. So remember, these Roman numerals, they indicate which ion it is. If it's copper 2, it means it's copper 2 plus. If it's copper with a 1, like that, if that was a bracket, that would be what? It would be copper 1 plus, okay? So in this case, we have copper 2 plus, as we've illustrated here. And because copper can form either copper 2 plus or copper plus, that is why we need this Roman numeral, because of the multiple ionic ions formed by copper. Okay? Yeah, show a different ion. However, what did we say? Group 1 metals always form the same ion, right? They always form ions with a positive charge. And that's why we don't need to know to show it with the Roman numerals, because it only forms this one ion. So therefore we know which ion we're talking about. Okay. So state how the physical properties of copper differ from those of sodium. What can you guys name? Oops. So copper 2 sulfate is blue. Alkali metals, they form colorless, so they form white compounds. And we'll have a long Kahoot tomorrow. Hard and strong, high density. Brilliant. So perfect. So your copper is much harder. Brilliant. It's also much higher density. Brilliant. Yeah. Perfect. High density, exactly. Okay. So how does the reactivity of copper compare with that of sodium? Use a test with water to illustrate your answer. Okay, so how does the reactivity of copper? So it's much less reactive with sodium's far more reactive than copper. And yeah, so copper will not react with water, but sodium, what's going to happen? Sodium will fizz, exactly. So sodium will straight away react and produce the hydrogen, which is fizzing that we see. Well done. Okay. Any questions for this part? No. Okay, so let's move on to the next question then. Because, okay, so now we've moved off from the transition metal topic. So now this is more of a recap from everything we've done so far. Tomorrow, there will be a lot of transition metal questions in the... So transition metals can react, but they just need more intense conditions. So like we said, if it reacts with chlorine, we'd need to heat it to high temperatures to cause the reaction, whilst say group 1 metals, they don't need any heat for them to react, which makes them super reactive. So it shows how reactive they are. Okay, so student investigated green ink using chromatography. So we're on paper chromatography. Set up the apparatus as shown in figure 2. So the first question is, what would have happened if the student had set the apparatus as shown in figure 2? So what is wrong with the apparatus in figure 2? Does anyone have any idea? So some questions. What colours do you need to know and how would you remember them? I don't think you need to know any colours at GCSEs. So the colours that were written in the textbook were about the copper sulfate being blue and the colours that you've seen on these slides. So if you want to go back on YouTube and look at them, you can jot those colours down, but I don't think you need to remember them. It might help in the exams. Will the copper still have a full outer shell? so you don't need to think about these full outer electrons when it comes to transition elements. You just need to know that they can form quite a few different ions. Why do we need to heat transition metals before reacting them? Because they're very unreactive. Heat helps with these reactions. So maybe you guys have burnt, so you probably have heated up stuff in your labs at school and then caused a reaction. So now let's see what. Yeah, brilliant. So lots of you guys have said the correct thing. Water is above the pencil line, exactly. So the solvent should always be below the dot, below this pencil line. Well done to everyone who came up with the answer. Great effort. Yeah, heat to reach the activation and the energy reaction. That's why you need to heat some reactions. Do we need to memorize the reactivity series? Well, you just need to know that transition metals are less reactive than group 1 because they're just not very reactive. You need to know that that group 1 metals are very reactive, as we've seen, and how they react with, say, water and oxygen, which you've come across. But it's not so, and then you just also need to know the trend that we did yesterday, the fact that down group 1, the reactivity increases. So those are sort of stuff to remember with this topic. Okay, so next question, sorry, still on the paper chromatography. Well, if you want to write down the minimum, the stuff to remember the reactivity series with, drop that in. Group 1 more reactive than group 7. You don't really need to think about it that way. So you don't compare group 7 to group 1 because group 7 is a non-metal and group 1 is a metal. So why should the line be drawn in pencil and not in ink? Well done to people who are answering that. Yeah, so perfect. The ink does dissolve in water, so the ink can flow up. Well done to everyone who got that answer. So now we've set the apparatus up correctly, and they see this. So what does figure 3 tell us about the green ink? Yeah, lots of correct answers in the chat. Question 2. Which part of question 2? Do you want me to explain? There's yellow and blue ink. Brilliant. Yeah, perfect. So it tells us that green ink is made up of yellow and blue. 2.3. Chromatography. So yeah, let's do question 3 now. Another student sets up the apparatus. Oh no, sorry. Question 4, why did the yellow dye move further up the paper? Exactly, because yellow is more soluble in the solvent. Brilliant, well done. So quick explanation of how chromatography works. So if we took this one, for example, you put on your green dot here, you put it in a beaker of your solvent, so in this case it's going to be water, and you need to make sure that your solvent is below this line. Then the solvent, it travels up the paper, and obviously this ink, it also travels up the paper with it, and then each different color travels up a different amount due to the difference in their solubility. Okay, that's why yellow moved up further. Sometimes you need to work out RF values in exams, but it will be obviously given, it will be asked for it, and yeah, hopefully you guys can remember from yesterday or the other day how to work those out. 2.1, someone wants me to explain 2.1. So describe what would have happened if the student had set the apparatus as shown in figure 2. So it's just incorrect. So this ink, it might have just dissolved into the water. It's just wrong because so the water starts here, so it starts traveling from up here, so it's not carried correctly. Whilst you want your water to move up from the bottom of the paper to the top and drag this ink with it. Okay. So 2.2, why should the line be drawn in pencil and not in ink? Yeah, so ink, it's soluble in water. So therefore, if you draw this line in ink, and maybe one day you might be able to try it at school, you'll see that the ink, it gets dragged upwards too. Pencil is not soluble in water, and so it will not flow up the paper, exactly. And I got it right. What would you say we do? What day did we do the RF? That was on Tuesday, 2 days ago. Yeah. Tuesday we did RF values. So retention factors. Okay, let's move on to, we can do some balanced equation practice, or what's the next question? Oh, periodic table, or we can look at the next question, or people prefer balanced equations or number 3. Is there any preference? 3, this one. Okay, both. Okay, we'll do this one, and then tomorrow we'll do more on balanced equations. So look at the table, the data in the table below. So what is the physical state of each element in the table at 25 degrees C? So for bromine, what do we think the physical state will be? Yeah, brilliant. Liquid it is. Okay, so because 25 degrees is in between these two temperatures, right? So it's greater than the melting point, so therefore it's going to be a liquid if it's greater than the melting point, but it's below the boiling point, so therefore it's also going to be a liquid. So if the temperature is above the boiling point, it's going to be a gas. If it's only above the melting point but below the boiling point, it's going to be a liquid, okay? So what about cesium? What is cesium? And if it's, so what is cesium going to be at room temperature? Solid, exactly. So 25 degrees is below the melting point temperature. So therefore it is a solid because it's not melted yet. So what about fluorine? What's fluorine going to be? Yeah, brilliant gas. Because 25 degrees is significantly higher than the boiling point. What about strontium? Yeah, brilliant. And the last one, xenon will be, so strontium will be a solid and xenon will be a gas, exactly, okay. So which elements exist as a liquid over the widest range of temperatures? So what is the question looking for here? Does anyone know? Yeah, brilliant. Strontium, perfect. So we're looking for something with the largest difference in between these two. So yeah, I think strontium has a higher difference than cesium, but you'd have to check that with a calculator. Yeah, perfect. Okay, so what is the chemical symbol for atoms of each element in the table? So how would we figure out what the symbols were if we didn't know them off by heart? Right. Bromium, Br for, yeah, perfect. Look on the periodic table. So where was that periodic table? So exactly. So if we find cesium was one of our words, wasn't it? So cesium down here, we look at cesium and we circle it exactly. So then for say xenon, we'd find xenon. So xenon is here, right? And we'd put Xe. Yeah, well done. So next one, classify each element in the table as a metal or a non-metal. So which ones do we think are metals? Do people want to jot that down? Which ones are non-metals? Yeah, good. Yeah, so cesium and strontium are the only metals. Yeah, brilliant. So only cesium and strontium are metals and the rest are non-metals. So write the electronic structure of a fluorine atom. So either we can draw it out or we can do the one with the numbers. So we're going to go for the one with the numbers. How do you know when an element is a metal and when not? Because of the staircase thing. So yeah, cesium and strontium. So one side of the periodic table are metals, one side are non-metals, but I'll show you quickly at the end. Yeah, brilliant. So the electronic structure is going to be 2, 7, 2 in its first shell, 7 in its second shell. And what's going to be the electronic structure of a fluoride ion? 2.28, brilliant. And yeah, they will 100% give you a periodic table in the exam. So key thing to remember, where are the non-metals? So if you draw on this line, your non-metals are this side, your metals are this side. Okay, so all of these are metals, these are non-metals. So that's how you can tell the difference. Okay, so I think we'll finish up here then. So tomorrow we're going to be doing more of a summary. We're going to be covering exam techniques, and we're going to be doing questions on all the topics we've done so far. So see you there tomorrow for our last lesson, and have a lovely evening. Bye.